Not real-time control using LabVIEW, but almost real-time control using LabVIEW. LabVIEW throughput measurements. Several options are compared in this video. There's the DAC Assistant using the PCI6025E card, and then low-level data acquisition using the PCI6025E. Differential versus reference single-ended. National Instruments USB6009 low-cost data acquisition. Then there's ELVIS 2 with analog input, ELVIS 2 with oscilloscope input, and with a primary focus on Arduino analog input and output under LabVIEW. All LabVIEW examples use one sample on demand. The computer is a Dell Optiplex 980 64-bit Windows 7 Service Pack 1 running 3.2 gigahertz. A quick overview using the PCI6025E. There's the DAC Assistant input, the DAC Assistant output, and a PID control block. Next, a low-level input and low-level output, also the PID control block. Next is low-level input, low-level output, but no PID block. Next is differential input, low-level I/O. Next is the USB6009 with low-level input and output. Now the ELVIS, low-level input and output with analog I/O. Now ELVIS with oscilloscope input. Now Arduino under LabVIEW. This is the getting started digital output. Arduino digital input and digital output. Arduino input frequencies 1 Hz, analog input, pulse width modulation output. Now Arduino low-pass RC filter with a corner of 440.8, now a corner of 90.7, now a corner of 408 Hz. Now a corner of 4 Hz. The input frequency is 0.465 Hz, a low-pass filter and with a corner of 4 Hz. Now change the input frequency to 4.1 Hz and keep the corner the same. Finally, the LabVIEW loop time is measured at 50 milliseconds using this VI. Now, all that remains is to summarize the significant features of each of these cases. Using the 6025E and LabVIEW DAC Assistant, 2.76 milliseconds is the delay, or the sample time. In all the oscilloscope examples that follow, the yellow signal is the input created by a function generator, and the green signal is the output created by the PCI6025E, the USB6009, NI-ELVIS, Arduino, or RC filter after the Arduino. Now 6025E using LabVIEW low-level I/O. Significant improvement, 0.7 milliseconds delay. .6025E using low-level I/O and the PID block removed. About the same delay time. Now the 6025E using low-level I/O and differential input versus reference single-ended. About the same delay time. Now switch to the USB6009 using low-level I/O and reference single-ended. 10 millisecond delay time. This delay is larger by a factor of 14.3. Now ELVIS. "28 millisecond delay. ELVIS is slower than the 609 and the 6025E. Now ELVIS using oscilloscope input versus analog input. 20 millisecond delay. ELVIS oscilloscope input is faster than ELVIS analog input. Now the Arduino driven by LabVIEW. No input signal yet. There's a LabVIEW input and Arduino output. LabVIEW virtual button activates an Arduino LED. Now Arduino using digital input and digital output. 1.25 Hz input signal and an I/O delay of 108 milliseconds. Output is reasonable but delayed if the input signal is less than 4.5 Hz. Here's the Arduino using analog input and pulse width modulation output. No low-pass RC filter yet. There's the input signal. There's the pulse width modulation output signal. Now include a low-pass RC filter at 40.8 Hertz corner frequency. .8 Hertz is too large. Make the corner frequency even larger, 90.7 Hertz. .7 Hertz is too large also. Now make the corner frequency even larger, 408 Hertz. .408 Hertz is way too large. Now use Arduino using a reasonable corner frequency, 4.08 Hertz, with a 1 Hertz input signal. The delay could be as much as 110 milliseconds. Here it's 78 milliseconds. The corner frequency is reasonable in this case. Arduino using the same 4.08 Hertz corner frequency but slower input signal, resulting in the same long delay. This combination would be a good design. Here's the Arduino using the same corner frequency but larger input frequency. Still has the same long delay. The long sample time distorts the input signal in LabVIEW, which results in an even more distorted output signal. And finally, the Arduino and LabVIEW loop time is measured at 50 milliseconds. In conclusion, here is the summary table. I hope you found this useful.